universal cycle of creation, where the demise of one universe marks the genesis of another. These theories are undeniably beautiful and captivating. However, there's a crucial caveat. Concrete evidence for any of them remains elusive. Black holes continue to guard their secrets fiercely. Unfortunately, delving into the secrets of these enigmatic behemoths of the cosmos presents formidable challenges. Studying black holes is no walk in the park. These cosmic entities are incredibly elusive. Black holes defy direct observation in the conventional sense. They don't emit light. Instead, they are the ultimate absorbers. Imagine a darkness so complete that it swallows everything, even light itself. This makes them virtually invisible to our telescopes, which rely on detecting light to perceive the universe. So, how do scientists even begin to study something that is, by its very nature, hidden? They must rely on indirect methods. The faint X-ray emissions emanating from the superheated material swirling around the black hole's edge offer clues. The way a black hole's immense gravity distorts the path of light and influences the motion of nearby stars provides another avenue for investigation. Black holes operate according to rules that often seem to defy our understanding of physics. They warp the very fabric of space and time, creating a mind-bending environment where the predictable laws of the universe break down. This makes it extraordinarily difficult to anticipate and fully grasp their behavior. But take heart, space enthusiasts. The future of black hole research is ablaze with promise. We have already achieved breakthroughs that were once considered impossible. Imagine, if you will, the year 2019. In that year, scientists captured the first ever direct image of a black hole. This wasn't just any black hole. It was the supermassive central black hole of the galaxy M87, a celestial titan located millions of light years away. Then, just a few years later, another triumph. We obtained an image of Sagittarius A, the black hole residing at the very heart of our own Milky Way galaxy. These images have unlocked entirely new pathways for research, allowing us to study these cosmic enigmas in unprecedented detail. And the discoveries don't stop there. Consider gravitational waves. Picture dropping a pebble into a still pond. Ripples spread outwards across the water's surface. Gravitational waves are analogous to these ripples, but instead of water, they propagate through the very fabric of spacetime itself. These waves are generated by the most cataclysmic events in the cosmos. The collision of black holes, the explosion of supernovae. They carry within them invaluable information, allowing us to listen to the universe in a way never before possible, revealing phenomena that were previously hidden from our view. All these observations provide scientists with new tools to study black holes, and as technology advances, our capabilities only increase. The James Webb Space Telescope, with its unparalleled sensitivity and resolution, promises to deliver even more detailed observations and deeper insights into the nature of these cosmic titans. There remains so much that we don't yet understand. But that is the essence of science. The thrill of the unknown, the insatiable curiosity that compels us to explore the mysteries of the universe. So, let us continue to peer into the cosmic abyss, driven by the thrilling quest to unlock the deepest secrets of our world. In its usual manner, you're simply relaxing, perhaps sipping a futuristic space lemonade as you watch the spaceship's voyage. For the people inside the spaceship, everything seems normal. Their watches tick at a regular pace, and they go about their daily routines without noticing anything unusual. However, from your objective viewpoint, it's as if you're watching the spaceship fall into a black hole in extreme slow motion. It might appear to you that it's been plummeting for weeks, months, or even years. You could celebrate your 80th birthday, and the spaceship would still be out there, inching closer. Incredible, isn't it? If time slows down for the spaceship, the light it emits also decelerates. Picture someone on that spaceship flicking a flashlight on and off. Because time is moving so incredibly slowly for them, the light emanating from the flashlight also moves in super slow motion from your perspective. It takes an eternity for each burst of light to reach your eyes. You'd be observing the spaceship as if you were watching a video in extreme slow motion. As light takes longer to travel to your eyes, it also weakens and becomes dimmer, like a fading star in the night sky. So, as the spaceship approaches the black hole's event horizon, the point of no return, it not only appears redder due to the extreme gravitational forces, but it also seems much dimmer. It becomes increasingly difficult to see the spaceship as it gets closer to the black hole. Slowly but surely, it fades away, like a grand disappearing act on the universe's most magnificent stage. It's a mind-boggling thought, but that's how it appears to an outside observer. But what about the people on board? What do they actually experience as they fall into a black hole? As they get closer, something truly bizarre begins to occur. The gravity near a black hole is so immensely powerful that it stretches and warps everything around it. The difference in gravitational pull between an astronaut's head and feet becomes significant. This disparity creates a tidal force, which elongates the body into a long, thin shape. This process is scientifically known as spaghettification. Essentially, the astronaut would be stretched into a human noodle. Being turned into spaghetti might sound amusing to a pasta enthusiast, but it's definitely not a pleasant experience for anyone unfortunate enough to fall into a black hole. Meanwhile, the colors surrounding the astronaut begin to warp and distort, creating a dazzling, otherworldly light show. It's akin to riding a roller coaster through a rainbow tunnel filled with twists, turns, flashes, and sparks. It's an exhilarating, mind-bending experience. Right before the end. And then, what happens next depends on the type of black hole the astronaut encounters. First, there are classical black holes. These are black holes that exist seemingly forever. If you fall into one of these, it would take an unimaginably long time to reach the center, the singularity. The singularity would keep getting closer and closer, but you would need an almost infinite amount of time to reach it. It would feel like your journey would never end. A truly terrifying prospect. Then, there are evaporating black holes. These black holes can, theoretically, evaporate over vast stretches of time due to a process called Hawking radiation. It's similar to ice cubes melting away. These black holes have a limited lifespan, and it's virtually impossible to fall into one. As you approach an evaporating black hole, you would find yourself hovering near its edge, the event horizon. It's like being stuck at the entrance to a super cool amusement park. But this amusement park is shrinking. The black hole is evaporating, and as it does, the event horizon gets smaller and smaller. You would stay right at the edge, tracking its every move. You would forever remain on this event horizon without ever crossing it, suspended for eternity. But remember, once you pass the point of no return, there's no way back. You're on a one-way ticket to the mysterious heart of the black hole. The singularity. At the singularity, everything goes haywire. Our current understanding of physics breaks down completely. It's akin to entering a magical realm where the rules of reality no longer apply. What happens once you reach the singularity? Is there anything on the other side of a black hole? We have absolutely no idea. It's a profound mystery for us. But perhaps someday, we will unlock the secrets of the singularity. So, my friend, it's best to admire black holes from a safe distance and allow your imagination to soar with the incredible wonders they hold. Just remember to keep your pasta on your plate and far away from these cosmic spaghetti makers. Imagine a celestial heavyweight, a star many times the size and mass of our own sun, locked in a deadly embrace with a cosmic anomaly, a black hole. Imagine a cosmic collision of unimaginable scale. A tiny black hole is hurtling through space, and its trajectory spells doom for our solar system. The question hangs in the balance. Can our sun, the source of all life on Earth, withstand the immense gravitational pull of this cosmic vacuum cleaner? Or will it be devoured, swallowed whole by this insatiable darkness? To understand the stakes, let's delve into the nature of these enigmatic entities. What exactly is a black hole? In essence, it's a region in space where gravity reigns supreme, so intense that nothing, not even light itself, can escape its grasp. Think of it as a cosmic drain, relentlessly sucking in anything that ventures too close. These celestial behemoths are so massive that they warp the very fabric of space-time around them, creating a distortion of reality. Black holes remain among the most terrifying and mysterious objects in the universe, a force of nature that challenges our understanding of physics, a true enigma. Black holes come in a variety of sizes. Some are relatively small, spanning only a few miles in diameter. Others are supermassive giants, boasting masses billions of times greater than our sun. Most black holes are born from the cataclysmic collapse of massive stars. After its birth, a black hole begins to grow, consuming everything in its path. And in a truly awe-inspiring spectacle, two or more black holes can collide and merge, forming a single, colossal cosmic monster in a terrifying dance of gravity. But what about these smaller black holes? The smallest known black holes are called stellar black holes. These cosmic entities typically possess a mass 3 to 10 times that of our sun. While that might sound substantial, consider this. It's like compressing all the matter in our entire solar system into a space the size of New York City. To put it in perspective, intermediate mass black holes range from 100 to 1,000 solar masses, while supermassive black holes can weigh millions or even billions of times more than our sun. In the grand scheme of the cosmos, stellar black holes are mere specks compared to their larger relatives. Imagine a star far larger than our own sun, its core a raging inferno of nuclear fusion. As the star exhausts its fuel, gravity begins to assert its dominance, relentlessly squeezing the stellar material. The more the star contracts, the hotter it becomes, until the core reaches temperatures of billions of degrees. Finally, the core collapses under its own immense gravity, triggering a colossal explosion known as a supernova. This violent implosion creates a singularity, a point of infinite density and gravity. Surrounding this singularity is the event horizon, an invisible boundary beyond which nothing, not even light, can escape. And just like that, a stellar black hole is born. A truly mind-blowing process. Stellar black holes are the most common type of black hole in the known universe. These cosmic entities are scattered throughout our galaxy. But what are the odds that one of these relatively small monsters will set its sights on our sun? And if such a cataclysmic event were to occur, what would become of us? In reality, the likelihood of the sun colliding with a black hole is astonishingly small. It's almost an impossibility. Even though stellar black holes are the most prevalent type of black hole in our universe, they are by no means common. The chances of the sun and a black hole crossing paths are so astronomically rare that it's akin to winning the intergalactic lottery. However, this is one lottery you definitely wouldn't want to win. As of 2023, the closest known black hole to our solar system is Gaia BH1. This black hole is estimated to be about 10 times more massive than our sun. Even so, it resides approximately 1/600 light-years away from us, a distance of trillions upon trillions of miles. Therefore, we can safely say that our sun isn't going anywhere anytime soon. But as the saying goes, never say never. Just as with any astronomical phenomenon, we must consider the various ways in which such a collision could potentially occur. For instance, it's conceivable that a rogue black hole could traverse our solar system, much like a comet or asteroid passing by. The problem is, unlike comets and asteroids, black holes are completely invisible. They can only be detected by their gravitational influence on surrounding objects. So, we wouldn't see a menacing black hole hurtling toward us. Instead, we would only become aware of its presence if it caused disturbances in the orbits of nearby celestial bodies. So, where does that leave us? We know that the sun is a massive, luminous star at the heart of our solar system. It's approximately 4.5 billion years old and possesses enough fuel to sustain itself for another 5 billion years. This star is so immense that its size almost defies comprehension. If you were to gather all the planets in our star, the sun, an incandescent giant, dwarfs everything in our solar system. Imagine trying to fit our entire solar system inside it. There would still be room to spare. The sun's mass is so immense, it constitutes nearly 100% of the total mass of the entire solar system. Therefore, it seems almost impossible to fathom how some insignificant little black hole, even 1,000 of times smaller than our sun, could possibly devour it. And you would be right, at least not entirely. Picture this. A rogue black hole has entered our solar system and is rapidly approaching the sun. As it draws nearer, the black hole's overwhelming gravity begins to rip material from the sun's surface. The sun itself begins to stretch and distort, a process known as spaghettification. Imagine a rubber band being pulled to its breaking point. That's analogous to what would happen to the sun. The stolen material will form a swirling vortex around the black hole, an accretion disk. As the black hole consumes more and more of the sun, this disk heats to unimaginable temperatures, emitting intense radiation. As the sun is torn apart, it would unleash colossal amounts of energy in the form of light and heat, becoming far brighter and hotter than ever before. The sun's outer layers would vaporize, creating an enormous cloud of gas and dust expanding outwards into space. It would be a cosmic fireworks display of unimaginable scale, but with catastrophic consequences. While the view would be one of the most spectacular in the universe, we wouldn't be around to witness it. As you might expect, Earth would be in for an incredibly rough ride. The intense radiation and solar material would ignite massive wildfires across the globe. The extreme heat would vaporize the oceans, turning Earth into a scorched wasteland. Our planet would be bombarded by a relentless stream of high-energy particles, ionizing the atmosphere. In short, the chances of any life surviving would be virtually zero. This collision would have far-reaching consequences, not just for Earth, but for the entire solar system. The relentless radiation and heat would vaporize everything in their path. The planets themselves would be torn apart and destroyed. Now, the sun, being a much larger object than a typical star, wouldn't be entirely consumed by the black hole. However, it would be severely distorted and disrupted. The black hole's immense gravity would tear away the sun's outer layers, triggering a massive explosion known as a tidal disruption event. Either way, in the end, the black hole would gain mass, growing in size, and a new accretion disk would form around it. As we have seen, the collision of the sun with a black hole, whether a small one or a stellar giant, would be an epic and catastrophic event. Thankfully, as we've already discussed, the likelihood of such a collision is extremely low. However, that doesn't mean we should cease our study of black holes and their potential impact on the universe. The more we learn about these enigmatic objects, the better prepared we'll be to understand and predict their behavior. So, let's continue researching, exploring, and observing the depths of space. Who knows, maybe one day we'll encounter a black hole that gets a little too curious and ventures too close to the sun. Let's hope that by then, we'll have already established colonies on distant planets. Now, surely an object possessing billions of times the mass of our sun would be easy to find, right? Unfortunately, it may not be that simple. Take the case of AEL 2261, a galaxy cluster believed to host a supermassive black hole at its center. Or at least, that's where it's supposed to be. The problem is, this gigantic cosmic phenomenon is nowhere to be found. Supermassive black holes are cosmic behemoths, slowly churning at the hearts of their host galaxies. They accumulate vast clouds of gas and dust, swelling to sizes that defy human comprehension. If a supermassive black hole, such as Sagittarius A, that resides at the center of our own Milky Way galaxy, were to move even slightly closer to our solar system, we would be doomed. Even at a distance of several dozen light-years, such a behemoth could wreak havoc on our planet. Earth, along with everything else in the solar system, would be dragged into the black hole's orbit, destined to spin around it, for eternity. Or longer. Who truly knows the extent of such cosmic forces? For now, it's fortunate that these cosmic vacuum cleaners remain at a safe distance. But what became of that rogue supermassive black hole ejected from a colossal galaxy cluster, some 2.7 billion light-years distant? Scientists have been diligently searching for it, using NASA's Chandra X-ray Observatory and the Hubble Space Telescope. But so far, their efforts have yielded no results. The inherent challenge lies in the very nature of black holes. They are, well, black. Compounding this is the fact that they reside in space, which is also black. This absence of contrast makes the task of spotting one incredibly difficult. Despite these obstacles, astronomers remain undeterred. They have a whole arsenal of technologies at their disposal to locate black holes, both large and small, scattered throughout the vastness of space. Some of these methods involve observing stars as they orbit these invisible giants. Others rely on detecting gravitational wave signals, the kind produced when two black holes collide. However, the most dependable technique involves watching as dust and gas spiral into their inevitable doom. Black holes, by their very nature, exert an immense gravitational pull. The regions of space surrounding them are often chaotic, swirling vortexes of matter. Gas and dust are inexorably drawn towards the bottomless abyss, compressed and heated to extreme temperatures in the process. This violent compression unleashes a torrent of X-ray radiation. Therefore, astronomers scan the cosmos for exceptionally bright X-ray sources, the likely death throes of colossal clumps of matter as they vanish into a black hole. So why can't scientists detect such X-ray signatures emanating from the suspected location of the missing black hole in Hubble 2261? One of the most baffling aspects of its disappearance is the detection by radio telescopes of massive plumes of superheated material ejected sometime within the last 50 million years. These plumes were almost certainly caused by a large black hole, a black hole that is now nowhere to be found. For the moment, all we can do is speculate. Perhaps two medium-sized black holes collided, the resulting merged giant receiving a kick that sent it hurtling out of the galaxy's center. Observations of the stars within that galaxy have revealed a dense clump of material located several thousand light-years from the galactic core. Could this be the runaway black hole? Regrettably, no X-ray signals are emanating from this clump. Alternatively, the black hole might still be there, lurking in its rightful place, but in a state of dormancy. If it's not receiving a steady supply of gas and dust, it has nothing to feed on. Consequently, it cannot release a flood of X-rays. But the explanation that we shouldn't disturb the sleeping giant isn't particularly satisfying. Why isn't it getting its usual meals? What happened 50 million years ago? And what is that clump of material that's speeding away from the galaxy's center? So many questions and so few answers, at least for now. Despite these mysteries, we at least have a general idea of what black holes look like, or rather, what their shadows look like. It's the shadow of the event horizon, the point of no return, silhouetted against the glowing superheated material as it plunges into the abyss. The first ever mugshot of a black hole was unveiled in 2019, although the data used to create it was collected in 2017. It took an international team of over 200 astronomers 2 years to assemble the image. We can marvel at this awe-inspiring cosmic phenomenon thanks to a vast global network of telescopes known as the Event Horizon Telescope Collaboration, or EHT for short. The name is derived from the fact that the event horizon represents the point of no return. When anything, matter, radiation, or even light, crosses this boundary, there is no escape from the black hole's relentless grip. To capture that groundbreaking image of a black hole, scientists essentially created a virtual telescope as big as the Earth itself, combining the power of 8 of the world's most powerful radio telescopes. It was no easy task. Researchers had to simultaneously point these telescopes in a meticulously planned sequence, relying on ultra-precise atomic clocks at each location. Moreover, to minimize the chances of rain and bad weather, they strategically placed the telescopes in exceptionally dry regions, such as the Atacama Desert in Chile and even the South Pole. On each day of observation, the telescopes gathered approximately 350 terabytes of data, 10 times the amount of data collected daily at the Large Hadron Collider. Black holes, the very words conjure images of cosmic mysteries and unimaginable forces. While supermassive black holes rightly grab headlines, there exists another class of these gravitational behemoths: stellar black holes. Smaller, yes, but arguably even more perilous. Let's journey to the death throes of a star. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own crushing gravity. The star collapses inward upon itself in a spectacular implosion. If the star was sufficiently massive to begin with, this implosion doesn't stop. It continues compressing and compressing until, voila, a stellar black hole is born. Don't let the term small fool you. A stellar black hole typically packs 5, perhaps even several tens, times the mass of our Sun into an incredibly compact space. And if that sounds intimidating, consider the hypothetical existence of mini black holes. These theoretical entities could be truly minuscule, no larger than a single atom. Yet such a micro black hole could possess the mass of 1,000 SUVs. Some theories propose that countless micro black holes were forged in the immediate aftermath of the Big Bang, during the universe's infancy. Some scientists even speculate that a few of these tiny terrors might be zipping through our planet every single day. Here in our own Milky Way galaxy, a supermassive black hole lurks at the very heart of it. This colossal object, known as Sagittarius A Gale, Sagittarius AA, boasts a mass equivalent to 4.3 million suns. But fear not, we won't be sucked into its abyss. Sagittarius A resides over 26,000 light-years from Earth, far too distant to exert any noticeable influence on our little corner of the cosmos. Intriguingly, astronomers have recently detected what appears to be a leak emanating from Sagittarius A. If confirmed, this suggests that it may not be the dormant giant we once believed. Perhaps Sagittarius A is still actively feeding, and this leakage represents the black hole hiccuping as it devours clouds of gas. Now, imagine yourself venturing near a black hole. Time itself would begin to warp and distort. For you, time would slow significantly, potentially offering a curious form of extended youth. However, beware. Do not cross the event horizon, the point of no return. Another danger of proximity to a black hole is its potential to erupt like a colossal galactic volcano. Instead of molten lava, these eruptions unleash tremendous amounts of energy, carving vast holes into the surrounding gas and matter. Not long ago, astronomers observed one of the largest craters ever seen in the universe. Using radio and X-ray telescopes, they detected the aftermath of a supermassive black hole that had thrown a cosmic tantrum eons ago. This event occurred in a galaxy cluster approximately 390 million light-years from Earth. The resulting void, a hole punched through the cluster's hot gas, is so immense that it could accommodate 15 Milky Way galaxies. Black holes remain an enigma, captivating scientists and sparking our imaginations. What lies within these cosmic abysses? A void? A bottomless pit? A gateway to another universe? The answers remain elusive, but scientists are continually developing new theories. Picture this. A massive star blazes across the cosmos, shining with the brilliance of a diamond. But as with all things, this stellar spectacle is finite. Eventually, the star exhausts its fuel reserves, its radiant existence drawing to a close in a cataclysmic finale. The star collapses under its own immense gravity, triggering a violent implosion. This implosion is so intense that it creates a sinkhole in spacetime, a black hole, the ultimate inescapable trap, relentlessly devouring everything in its vicinity, even light itself. Envision yourself approaching a black hole. The black hole itself emits no light, but you'd witness a breathtaking display of cosmic fireworks surrounding it, the accretion disk. This swirling vortex of gas and dust, pulled in by the black hole's immense gravity, forms a celestial carousel, a mesmerizing dance of matter spiraling toward oblivion. Temperatures in this region soar to millions of degrees, bathed in intense X-rays and high-energy radiation, detectable only by telescopes far away on Earth. But imagine, against all odds, that you somehow survive this hellish environment. As you draw closer, you encounter a mysterious boundary, a point of no return, the event horizon. Beyond this threshold, the known laws of physics seem to break down. You're now caught in a cosmic traffic jam. No matter how hard you accelerate, you're going nowhere. Once you cross the event horizon, there's no escape from the black hole's relentless grip. Imagine stepping across a boundary from which even light itself cannot escape. You are now inevitably drawn into the gravitational abyss of a black hole. What would you witness in your final moments? According to the brilliant mind of Albert Einstein, Space and time are not separate entities. Instead, they are interwoven into a single fabric known as spacetime. Think of it as a vast, cosmic trampoline, capable of stretching and bending under immense weight. Black holes, with their unfathomable density, warp this space-time fabric in the most extreme way imaginable. As you approach a black hole, prepare for a mind-bending roller coaster. The curvature of space-time intensifies to an almost incomprehensible degree, creating a vortex that pulls everything inexorably inward, even light itself. The cosmos around you transforms into a bizarre funhouse, with colors distorted and light rays twisting and shifting in impossible ways. You might feel as though you're trying to moonwalk on a never-ending treadmill. Furthermore, the extreme curvature of space-time near a black hole gives rise to a phenomenon called time dilation. Time itself flows at a different rate in the vicinity of the black hole compared to the rest of the universe. The closer you get, the slower time seems to pass, like watching the world in slow motion. The deeper you plunge, the more reality unravels, and the very laws of physics appear to break down before your eyes. But let's assume, against all odds, that you somehow survive this descent into madness. Where exactly are you falling? What awaits you on the other side? Is there even another side? As you journey deeper into this celestial maelstrom, you eventually reach an elusive and utterly mysterious point known as the singularity. This is the heart of the black hole, a place where all matter and energy are crushed into an infinitely small point of unimaginable density. Try to imagine the mass of entire stars compressed into something the size of a pinprick. Here, the familiar rules of physics cease to apply. You have entered a realm where the known dissolves and the unknown reigns supreme. So, what does this unknown realm look like? Several fascinating theories attempt to describe the indescribable. Perhaps the singularity is a gateway to other dimensions. What if multiple universes are nested within black holes, like Matryoshka dolls? According to this theory, the interior of a black hole could be a portal to a parallel universe, governed by its own unique set of physical laws and possibilities. This parallel universe could be radically different from our own, a truly mind-boggling concept. Or consider the possibility of wormholes. Imagine black holes as components of a vast, cosmic subway system, connecting disparate regions of space and time. These theories propose that the immense gravitational forces within a black hole could create a wormhole, a tunnel offering passage to another galaxy, or even to the distant past or future. It's like discovering a secret passage in a video game, one that leads to an entirely new level. But there's more. Some scientists speculate that within a black hole, we might encounter exotic matter, perhaps strange matter with bizarre properties, or even negative energy density. Such a discovery would challenge our fundamental understanding of the universe. Finally, one of the most mind-bending theories suggests that a black hole could actually lead to a white hole. Imagine falling deeper and deeper, only to suddenly find yourself ejected into a blindingly bright space. You have entered a white hole, a cosmic fountain spewing matter, energy, and information into the universe with reckless abandon. It could be the birthplace of new universes. While black holes are defined by their event horizons, white holes possess an anti-event horizon. Black holes allow everything to enter, but nothing to escape. White holes conversely repel everything. White holes remain hypothetical objects. Their existence is yet to be definitively proven. Yet if they do exist, they could be intimately connected to black holes. It stands to reason. Black holes draw everything in, and white holes must obtain their matter from somewhere. The matter and energy pouring out of a white hole could potentially give rise to new universes. Together, black holes and white holes could form as set with us to the heart of a distant galaxy known as Sears 1019. Here, nestled within its cosmic embrace, lies a black hole of peculiar distinction: music. This black hole, Sears 1019, defies expectations. It's surprisingly diminutive, a cosmic infant in a universe of giants. Its mass, equivalent to roughly 9 million suns, might sound colossal, but in the grand scheme of supermassive black holes, it's a mere speck. These behemoths typically swell to billions of times the mass of our own star. But the anomalies don't end there. Scientists are grappling with a perplexing question. How did Sears 1019 reach its current size in such a short cosmic time span? The conventional understanding dictates that supermassive black holes require eons, far longer than 600 million years, to attain their full stature. Their growth is fueled by two primary mechanisms: the insatiable consumption of surrounding matter and the cataclysmic merger with another black hole. Even black holes akin to Sagittarius A, the one residing at the center of our Milky Way, boasting a mass of 4.3 million suns, are expected to appear in more recent epochs of the universe. Music. In fact, astronomers have long theorized the existence of supermassive black holes in the early universe. Now, thanks to the James Webb Space Telescope, JWST, and its infrared vision, this theory has been substantiated. The JWST has revealed that Sears 1019 is actively devouring any matter it can grasp. Such ravenous black holes are typically enveloped by swirling clouds of gas and dust, known as accretion disks, spiraling inexorably towards their doom. The immense gravitational forces at play heat this matter to extreme temperatures, causing the disk to radiate intensely. And there's more. The process generates extraordinarily powerful magnetic fields that channel matter towards the poles of the black hole. Periodically, this matter is ejected into space as twin high-energy jets. These jets hurtle outwards at velocities approaching the speed of light, creating dazzlingly bright emissions. Music astronomers were scrutinizing the galaxy, hosting this ancient black hole as part of the Cosmic Evolution Early Release Science, SEERS, survey. They observed the galaxy as it existed when our 13.8 billion-year-old universe was a mere 570 million years old. In addition to this primordial black hole, scientists detected two others, likely formed 1 and 1.1 billion years after the Big Bang. Their investigations also unearthed 11 ancient galaxies dating back to between 470 and 675 million years after the dawn of cosmic history. Now, let's shift our focus to the titans of the cosmos, the largest black holes ever discovered. What would happen if one of these behemoths wandered into our solar system? NGC 6166 is a true leviathan, amassing a mass equivalent to 30 billion suns. It resides within an elliptical galaxy characterized by an active galactic nucleus. Furthermore, it stands out as one of the brightest sources of X-rays known to exist. The supermassive black hole at the heart of NGC 6166 drives two symmetrical radio jets in opposing directions, a consequence of gas plummeting into its center. Another intriguing aspect of NGC 6166 is its blue shift, indicating that it's moving towards us. Is it time to prepare for the evacuation of our solar system? Our next stop takes us to the constellation Draco, approximately 10.4 billion light-years away. Here lies a supergiant black hole with a mass exceeding 30 billion suns. Besides its staggering mass, this black hole is physically enormous. If it were to replace our Sun, its diameter would extend beyond the orbit of Pluto, engulfing our entire solar system. The following black hole is among the most captivating on our list. It possesses a mass of 40 billion suns and is classified as a blazar, the most energetic type of quasar, those exceptionally luminous and distant objects. This blazar's luminosity is a staggering 300 trillion times that of our Sun, and more than 25,000 times the combined luminosity of all the 100 to 400 billion stars in the Milky Way galaxy. However, its immense distance of about 12.1 billion light-years prevents us from directly observing it. Nevertheless, we know that the central black hole of this quasar devours gargantuan quantities of matter, consuming approximately 4,000 solar masses of material each year. IC 1101 is a supergiant elliptical galaxy. It reigns as the most massive galaxy known to us. Being an elliptical galaxy, it contains relatively little gas, resulting in a low rate of star formation. As for the black hole at its center, its mass is estimated to be in the range of 40 to 100 billion suns, and it emits strong radio signals. But the biggest is yet to come. Imagine, if you will, a cosmic titan, a gravitational monstrosity, dwarfing anything we can readily comprehend. Scientists have recently turned their gaze toward a black hole of truly unimaginable scale. TON 618. This behemoth isn't just big, it's an astounding 66 billion times the mass of our Sun. Yes, you heard that right. 66 billion solar masses. To put that into perspective, imagine gathering every single star in our own Milky Way galaxy, compressing all of their matter into a single point. Even then, you wouldn't have enough to create a TON 618. If this colossal black hole somehow replaced our Sun, its event horizon, the point of no return, would extend far beyond the orbit of Neptune, more than 40 times that distance. That's how vast this thing is. Now, while black holes possess immense gravitational pull, the image of them as cosmic vacuum cleaners, relentlessly devouring everything in their path, is a misconception. TON 618, for instance, still resides within a galaxy teeming with stars and other celestial objects, all peacefully orbiting it without being sucked in. The reality is, growing a black hole to such epic proportions is an incredibly difficult feat. But what if a supermassive black hole, similar to the one lurking at the heart of our Milky Way, decided to move a little closer to home, to our solar system? The answer, in short, is catastrophic. Even at a distance of several dozen light-years, such a behemoth would wreak havoc on a scale that's hard to imagine. Earth, along with all the other planets and objects in our solar system, would be inexorably drawn into its orbit, doomed to eternally circle this cosmic abyss. But for now, we can breathe a sigh of relief. Black holes of that magnitude are staying put at a safe distance. In recent news, the James Webb Space Telescope, a technological marvel about 100 times more powerful than its predecessor, the Hubble Space Telescope, has achieved an extraordinary feat. While Hubble peered into the cosmos to distances of approximately 13 billion light-years, James Webb has surpassed even that. It has detected something truly unexpected, a supermassive black hole from a time when the universe was a mere infant, less than 600 million years old. This is the most distant, actively feeding supermassive black hole ever observed. Designated Sears 1019, this black hole resides at the center of its host galaxy. What's particularly intriguing is that it's also one of the smallest and least massive black holes discovered in the early universe, clocking in at a mere 9 million solar masses. While 9 million suns might sound like a lot, supermassive black holes often swell to billions of times the mass of our own star. So, what makes this find so unusual? And why are scientists struggling to explain it? The problem lies in the timeline. Current theories suggest it should take far longer than 600 million years for a supermassive black hole to attain such a size. These behemoths typically grow by either consuming surrounding matter or merging with other smaller black holes. Even black holes similar to Sagittarius A, the one at the center of our Milky Way, which is almost 4.5 million times the mass of our Sun, were expected to be seen in the more evolved, more recent universe. Scientists have long suspected that supermassive black holes might have existed in the early universe, but this theory has only now been confirmed thanks to the James Webb Space Telescope and its infrared capabilities. The observations show that Sears 1019 is actively consuming vast amounts of matter. Such actively feeding black holes are typically surrounded by swirling clouds of gas and dust, known as accretion disks, spiraling inward. The immense gravitational forces at play heat this matter to incredible temperatures, causing the disk to glow with intense brightness like a cosmic diamond. Furthermore, the process generates powerful magnetic fields that channel matter towards the black hole's poles. From time to time, this matter is violently ejected in the form of twin jets, traveling at speeds approaching the speed of light. These jets emit incredibly bright light, making them visible across vast distances. Astronomers observed the galaxy hosting this ancient black hole as part of the cosmic evolution. Early release Science, Sears survey. They saw the galaxy as it existed when the universe, which is now around 13.8 billion years old, was only 570 million years old. In addition to the primary focus of this observation, scientists also identified two other black holes, likely formed. Imagine a mind-bending concept. What if the cosmos we inhabit, with all its stars and galaxies, is actually contained within a black hole? This is the core idea behind black hole cosmology, a theory that proposes our observable universe is nestled inside a black hole, residing within a larger parent universe, or perhaps even a vast multiverse. And that multiverse, in turn, could be part of an even grander structure, a cosmic set of Russian nesting dolls. It might sound like pure science fiction, but this idea stems from some intriguing observations. When scientists reconstruct the timeline of our universe, they arrive at a point of origin called a singularity. Picture squeezing a massive ball smaller and smaller. Eventually, it would reach an incredibly dense state just before collapsing completely. While difficult to imagine in the realm of space, it's theoretically possible to compress an immense amount of mass into an infinitesimally small point. This is a singularity, where matter is crushed into a space smaller than an atom, yet it retains the mass of everything. Within this singularity, the known laws of physics cease to apply. Concepts like time, space, and matter break down, rendering our understanding obsolete. Scientists theorize that this singularity was the starting point of our universe, the moment of the Big Bang. This minuscule point, packed with everything, rapidly expanded, giving birth to the universe we observe today. Intriguingly, scientists also believe that singularities exist deep within black holes. According to Einstein's theory of general relativity, a black hole forms when a massive object, like a colossal star, collapses under its own gravity. The more massive an object, the stronger its gravitational pull. A star many times larger than our Sun would possess such immense gravity that it begins to draw in everything around it, warping the fabric of space-time to such an extent that it appears as a hole in space. This central point, where everything falls and is crushed into infinite density, is the black hole's singularity. Could our entire universe, then, be a tiny singularity residing within an enormous black hole in another universe? It's a provocative thought, but compressing something to the point where it warps space-time isn't easy. It requires extreme compression. To create a black hole the size of a human, you'd have to compress that person down to the size of an atomic nucleus. A black hole the size of a chickpea would require compressing the entire planet Earth to that size. However, our universe is mostly empty space. The vast distances between stars span trillions of miles of nothingness. If you were to compress all the matter in the universe, galaxies, stars, planets, dust, it would surprisingly occupy a relatively small volume, about 1 billion cubic light-years, forming a cube roughly 1,000 light-years on each side. Compared to the Milky Way galaxy alone, which is 100,000 light-years across, the universe is incredibly sparse. Despite this sparseness, the resulting compressed matter would be incredibly massive, likely collapsing into a black hole. And here's where it gets truly mind-blowing. This black hole would be approximately the same size as the original universe, possessing the same mass, energy, and average density. The size or radius of a black hole increases with its mass. The more it consumes, the larger it becomes. However, its density decreases as it grows. For a black hole the size of our entire universe, it would be relatively sparse. This isn't the only cosmic coincidence. Consider the Hubble radius, also known as the cosmological event horizon. Imagine our observable universe as a giant bubble. Its edge represents the farthest point we can see. When you stand in a field and look as far as you can, your vision traces a circle. The cosmological event horizon is similar. There might be more beyond it, but we can never know. Beyond this horizon, light from distant parts of the universe will never reach us. Light travels at a finite speed, and the space between us and those distant regions is expanding too rapidly. It's like running towards something that's constantly moving further away. Imagine standing on the surface of a world, the wind howling with incredible force, threatening to tear you from your very spot. But we remain grounded, tethered to Earth, forever separated from those distant cosmic shores. Now let's consider the enigmatic black hole. These cosmic vacuum cleaners possess something remarkably similar to this earthly phenomenon. The event horizon, also known as the Schwarzschild radius. Think of it as the point of no return, an invisible boundary often depicted as a luminous ring encircling the black hole. Anything that crosses this threshold, matter, light, information, is irretrievably lost, swallowed by the black hole's immense gravitational pull. They are perfect cosmic garbage disposals. Interestingly, if we were to hypothetically create a black hole the size of our entire universe, it would possess the same mass and event horizon radius as our universe. Some scientists dismiss this as mere coincidence, while others propose a far more radical idea. Could our universe actually reside within a black hole? This mind-bending theory suggests our universe might not be alone. Instead, it could be one of countless universes, each existing within its own black hole, scattered throughout a vast multiverse. In this dizzying model, every black hole, both in our universe and in a parent universe, could give rise to a new universe, each governed by its own unique set of physical laws and structures. Quite a cosmic family tree. There's also the Einstein-Cartan theory, which offers a different perspective on the singularity at the heart of a black hole. Instead of collapsing into an infinitely dense point, the matter might create a wormhole, a tunnel through the fabric of spacetime. This wormhole, also known as an Einstein-Rosen bridge, could connect two distant points within our universe. In this scenario, one end of the wormhole is the black hole, while the other end could be a completely new universe in the process of being born. Imagine it as a cosmic teleporter. Cross the event horizon, and you're instantly transported to a new reality. Of course, if there's an entrance, there must be an exit. Some scientists have theorized the existence of a white hole, a hypothetical counterpart to the black hole. A white hole, as far as we know, doesn't exist, but if it did, it would be a region of space where matter is constantly ejected rather than pulled in. Imagine trying to throw something into it. It would be instantly repelled. These concepts all tie into the Big Bounce theory. This theory proposes that our universe didn't originate from a singular Big Bang, but rather from the rebound of a previous universe that had collapsed. Remember the analogy of a squeezed ball? Perhaps a previous universe was compressed to an incredibly small size before bouncing back and expanding, giving rise to our own. Thus, instead of being born from nothing, our universe might be a recycled version of a previous one. Then, there's shockwave cosmology. This theory suggests that the Big Bang might have been triggered by an explosion within a black hole, creating the expanding universe we observe today. As the universe expands and its density decreases, the black hole could eventually transform into a white hole, reversing its function and expelling matter instead of drawing it in. While these connections are intriguing, it's crucial to remember that they remain theoretical. Currently, there are no experiments or observations that can definitively prove or disprove these fascinating ideas. For now, they remain in the realm of speculation, but the speculation is certainly fun. Speaking of things we've been getting wrong, it turns out we've been mispronouncing Uranus, all this time. Astronomers say the correct pronunciation is Uranus, not Uranus. A subtle difference perhaps, but significant nonetheless. Interestingly, Uranus was originally proposed to be named George, after King George III. Imagine, a planet with a majestic, kingly name. Ultimately, the astronomers changed their minds. And now it's the punchline of every joke. Consider the sheer cost of launching missions into space. If you divide the total cost by the weight of the cargo, the numbers are staggering. Back in 2016, specialists estimated it cost $110,000 to send a single pound of cargo into space. Now, the prices have skyrocketed. Sending cargo aboard a Cygnus spacecraft costs over $43,000 per pound, while SpaceX's new carriers come in at around $27,000 per pound. Suddenly, that $5 bottle of water at the airport doesn't seem so outrageous, does it? Imagine venturing into the cosmos, where even a simple bottle of water becomes a luxury. Current estimates suggest that delivering a single bottle of water to space could cost anywhere from $9,000 to a staggering $43,000. But fear not, space explorers, for the universe holds a secret. It was once believed that water was scarce beyond Earth, but reality paints a different picture. Water ice is abundant throughout our solar system. Forget those overpriced water bottles. Cosmic ice lurks in comets, asteroids, and even within the Ultimate Union. We'll delve deeper into that process later. But first, let's consider how these smaller stellar black holes come to be. As massive stars reach the twilight of their existence, they undergo dramatic transformations. They swell in size, shedding vast amounts of their mass and cooling down to eventually become what we call white dwarfs. However, some particularly massive stars, such as the progenitor of Gaia BH3, are thought to have a different fate. These stars, often lacking in heavy elements, what astronomers call metal poor, don't lose as much mass during their life cycle. Instead of gently fading into a white dwarf, they experience a catastrophic collapse, imploding to form a black hole. The companion star to Gaia BH3, being very metal poor, lends credence to the theory that the black hole itself formed from a similar star. To date, astronomers have identified around 50 stellar black holes scattered throughout the Milky Way. But the universe is far from uniform. Some black holes are significantly larger than others. These cosmic vacuum cleaners are sprinkled throughout galaxies, each with its own size and mass. The true giants, the supermassive black holes, reside at the very centers of galaxies, exerting immense gravitational influence on everything around them. While stellar black holes typically possess a mass only a few times greater than our Sun, these supermassive monsters can weigh as much as 1,000,000 to 1,000,000,000 suns. Yet despite their immense mass, they are compressed into a relatively small area, perhaps no larger than our solar system. How do these supermassive black holes form? Some astronomers propose that they arise from the simultaneous collision and collapse of multiple stars. Others suggest that these behemoths began as tiny seeds billions of years ago, gradually accumulating mass through a process called accretion, essentially gobbling up all the matter in their vicinity. Despite our growing understanding of black holes, fundamental questions remain. One of the most perplexing is the black hole information paradox. If a black hole possesses mass, and they certainly do in abundance, then, according to the laws of thermodynamics, it must also have a temperature and radiate heat. The renowned physicist Stephen Hawking demonstrated that black holes should emit radiation, now known as Hawking radiation, from their boundary. However, Hawking also pointed out a troubling paradox. If a black hole can evaporate, does that mean the information it contains is lost forever? The problem lies in the fact that the thermal radiation emitted by a black hole is degraded. It doesn't carry any discernible information about the matter that the black hole consumed. This irreversible loss of information clashes with one of the core principles of quantum mechanics: that physical systems evolving over time cannot create or destroy information. Something, it seems, is missing from our understanding. Physicists and mathematicians have wrestled with this paradox, proposing various solutions, some of which lead to bizarre conclusions. One such idea suggests that the universe might be holographic, meaning that what we perceive as our universe is actually a projection from some distant, interacting boundary. Indeed, black holes are strange and perplexing, yet we have compelling evidence for their existence. Take, for instance, the image of the black hole M87 Themis. It certainly appears to be a physical object. But what if black holes, as we understand them, don't exist at all? An intriguing alternative theory proposes the existence of gravastars, hybrid objects composed of gravity, vacuum, and stellar matter. This idea, first put forth in 2001 by Emil Motola and Paul Mazur, suggests that during the collapse of a massive star, intense gravity might transform its matter into an exotic new state. This is somewhat analogous to what happens when atoms are cooled to extremely low energy levels, causing them to behave as a single unified superatom. In the context of gravastars, a collapsing star might— imagine a star collapsing under its own immense gravity, reaching the point of no return, the event horizon. But what if, instead of forming an infinitely dense singularity, its matter transforms into an entirely new state? This is the premise of gravastars. Picture this: immense outward pressure counteracting the relentless crush of gravity, preventing the star from collapsing into that physics-defying point. In the gravastar theory, an ultra-thin, ultra-cold, and ultra-dark, virtually indestructible shell surrounds a core of heavily warped spacetime. This exotic new form of matter proves incredibly durable, yet possesses a certain flexibility, much like a bubble. Anything unfortunate enough to be trapped within the gravastar's intense gravitational field and smashed against this shell is instantly obliterated and assimilated into the very structure of this bizarre celestial object. One significant advantage of the gravastar hypothesis is that it neatly sidesteps the thorny paradoxes associated with information loss and singularities within black holes. Despite its intriguing nature, the gravastar theory falls short of fully explaining all the phenomena we observe in the cosmos. After all, we've directly observed objects that behave remarkably like black holes. Consider the shadow cast by these objects. It's not solely due to light being trapped by an event horizon. A related phenomenon, known as gravitational redshift, also plays a crucial role. Gravitational redshift causes light to lose energy as it traverses regions of intense gravitational fields. A gravastar could potentially mimic this effect. Light emitted from areas close to these alternative objects might lose so much energy to the gravitational field that by the time it reaches our telescopes, it appears as a shadow. Just as with black holes, things become considerably more complex when rotation is factored in. Many experts believe that gravastars would likely be unable to maintain stability while rotating at high speeds. But the strangeness doesn't end there. Some theories propose that the interior of a gravastar might consist of a series of nested shells, akin to a matryoshka doll. These hypothetical structures are known as nest stars. Of course, these theories are still in their infancy. Astronomers face a considerable challenge in developing fully functional models. There's even the possibility that both black holes and gravastars exist in the universe. This, however, presents another conundrum. How do we distinguish between the two? Some theories suggest that these different types of space objects should emit distinctly different gravitational waves. Such differences in gravitational radiation could provide a means to identify whether we are observing a gravastar or a traditional black hole. Black holes themselves are among the most massive and densest objects known. Their gravitational pull is so overwhelming that nothing, not even light, can escape their grasp. But within this already terrifying realm of black holes, there exist true behemoths, entities in a league of their own. Recently, astronomers discovered a black hole with a mass 33 billion times that of our Sun. This colossal space giant resides at the heart of a supergiant elliptical galaxy called Abell 1201, located approximately 2.7 billion light-years from Earth. This black hole is so immense that it has been granted the rare designation of an ultramassive black hole. It dwarfs the supermassive black hole at the center of our own Milky Way galaxy, exceeding its mass by a factor of more than 8,000. This ultramassive black hole holds the distinction of being the first to be discovered through the technique of gravitational lensing. This method relies on the principle that extremely massive objects, such as galaxies, can bend and magnify the light emanating from more distant objects situated behind them. A significant advantage of gravitational lensing is its ability to allow astronomers to study inactive black holes, those that are not actively consuming matter. This opens up the possibility of detecting countless new black holes throughout the universe, even in regions far beyond our own galaxy. Such discoveries could potentially reveal exotic objects unlike anything we have ever encountered. Now, let's turn our attention to another incredible instrument that is revolutionizing our exploration of space: the James Webb Space Telescope. When this remarkable telescope gazes upon young galaxies, which might appear as mere red specks through other instruments, it unveils an astonishing number of active galactic nuclei swirling at their centers. These are supermassive black holes in the process of formation. Intriguingly, giant black holes are believed to have played a significant role in the early history of the cosmos. The James Webb Telescope is consistently revealing an unexpected abundance of these cosmic beasts. For instance, astronomers have employed the telescope to detect a supermassive black hole that existed when the universe was less than 600 million years old. In cosmological terms, this is practically an infant. This is the most distant actively feeding supermassive black hole ever observed, a window into the universe's distant past. Journey, around 1.1 billion years after the Big Bang, as well as 11 ancient galaxies dating back to between 470 and 670 million years after the universe's birth. The exploration of the ancient universe continues. Imagine traveling back to the dawn of time, just 5 million years after the universe exploded into existence. What's truly astonishing is that, until very recently, our understanding of the early cosmos was almost entirely theoretical. Now, thanks to the revolutionary James Webb Telescope, astronomers can gaze upon galaxies and black holes at unimaginable distances, and crucially, they can measure them. But this is just one piece of the puzzle in the ongoing black hole saga. Recently, scientists observed something extraordinary. Two stars seemingly slowing down as they orbited a black hole. The explanation? It's likely the result of drag, a cosmic friction produced by dark matter. This could be the first tantalizing evidence that enormous quantities of dark matter envelop these enigmatic celestial objects. So, what exactly is this dark matter? This mysterious substance that dominates the universe? Our cosmos is composed of three primary ingredients: normal matter, dark matter, and dark energy. Normal matter, everything we can see, touch, or detect with our instruments, accounts for a mere 5% of the universe. Perhaps normal isn't quite the right term. Dark energy, the force driving the universe's accelerating expansion, makes up a staggering 68%, while dark matter comprises about 27%. This dark matter remains one of the greatest enigmas in the cosmos, baffling scientists to no end. While dark energy propels the universe outward, dark matter is believed to be the invisible scaffolding that holds galaxies together. Potential candidates for dark matter range from exotic, undiscovered particles to incredibly faint, dim objects. While the precise nature of dark matter eludes us, astronomers are certain about what it is not. It's dark, so we can rule out visible stars and planets. It can't be dark clouds of normal matter, as those would be detectable. Dark matter isn't antimatter, because we don't observe the telltale gamma rays produced when antimatter annihilates with ordinary matter, and it's not simply gigantic, galaxy-sized black holes. In essence, dark matter remains as profound a mystery as dark energy. However, let's return to the potential discovery of dark matter surrounding black holes. If confirmed, this would represent a monumental leap forward in dark matter research. The key lies in the fact that dark matter interacts gravitationally, exerting an influence on ordinary matter. A dedicated team of researchers meticulously observed the orbits of two stars, noticing a minuscule decay of about 1 millisecond per year as they danced around their black hole companion. The scientists concluded that these subtle changes in speed were caused by dark matter, generating friction and a drag force on the stars. Using sophisticated computer simulations of these black hole systems, the team tested a model widely accepted in cosmology: the dark matter dynamic friction model. This model predicts a specific loss of momentum for objects interacting gravitationally with dark matter. And the results? The simulation aligned perfectly with the observed data. This groundbreaking research provides compelling evidence for a long-standing theory that black holes can, in fact, swallow dark matter that ventures too close. As a result, dark matter becomes redistributed around black holes, creating regions of varying densities that can subtly alter the orbits of nearby objects, such as the stars we've been discussing. Speaking of black holes, there's an intriguing hypothesis suggesting that primordial black holes could actually constitute dark matter. These hypothetical black holes are relics from the universe's earliest moments. Scientists have yet to find definitive proof of their existence, but the theory is compelling. These primordial black holes would be incredibly ancient and remarkably small by black hole standards. Astronomers believe they may have formed within milliseconds after the Big Bang, before stars and galaxies even existed. This means primordial black holes would have witnessed the entire cosmic history unfold. The smallest of these primordial black holes would have likely evaporated by now, but larger ones could still be scattered throughout the vastness of space. If primordial black holes did exist, they could have arisen from regions of space where conditions were highly variable, some areas scorching hot, others relatively cool, and still others incredibly dense. Scientists theorize that these extremely dense regions could have collapsed under their own gravity, forming primordial black holes. Perhaps the most fascinating aspect is the potential size of these black holes. They might be incredibly small precisely because they originated so soon after the Big Bang. The universe was a vastly different place then. The longer the gestation period of a black hole, the more colossal its proportions become. The disparity in mass between these ancient, diminutive black holes and their more youthful, gargantuan counterparts is simply staggering. We're talking about a mass differential that could be 1,000 times greater than our own sun, an almost unfathomable figure. For decades, the notion that primordial black holes might constitute dark matter, or even be one and the same, remained on the fringes of scientific thought. However, recent discoveries have revealed a far greater abundance of black holes scattered throughout the cosmos than previously imagined. This revelation has breathed new life into the theory, suggesting that the vast, still hidden population of these Big Bang-born black holes could indeed account for the elusive dark matter. Think about it. Despite decades of relentless searching, astronomers have yet to capture even a single dark matter particle. Now, you might assume that plunging into a black hole is as straightforward as tumbling into a deep abyss. But believe me, it's a cosmic ballet of unimaginable complexity. To actually embark on a journey into a black hole, you'd need a confluence of extraordinary luck and perhaps a touch of cosmic sorcery. Moreover, if you were an observer, witnessing something being drawn into a black hole, you wouldn't even see it happen. Let's delve into the mesmerizing realm of physics to unravel this enigma. Falling into a black hole is an endeavor fraught with peril. First and foremost, to even stand a chance, your trajectory would need to be impeccably precise. Imagine trying to strike a minuscule target from an astronomical distance. Black holes reside within galaxies, swirling vortexes teeming with celestial bodies, stars, planets, and colossal clouds of gas. Each of these objects possesses its own gravitational field, capable of deflecting your course. It's akin to navigating a crowded room, dodging collisions, and resisting the gravitational pull of passers-by. As you approach the black hole, the challenge intensifies exponentially. Even the slightest directional adjustment would demand an insurmountable expenditure of energy, like trying to maneuver a spacecraft on empty. This is due to the black hole's insatiable gravitational appetite. Once you breach the event horizon, the point of no return, there's no hope of escape. Control becomes an illusion. Even if you were to miraculously navigate the treacherous path and evade every obstacle, a fiery gauntlet awaits. The searing heat and energy of the plasma surrounding the black hole. You'd be incinerated long before reaching the event horizon, unless shielded by some form of invulnerable protection. But the paradox deepens. Not only is falling into a black hole nearly impossible, but witnessing such an event is equally unattainable. Picture yourself as a distant observer, watching a spaceship hurtling towards a black hole's event horizon. As the craft approaches its doom, two bizarre phenomena begin to unfold. First, the color of the spaceship undergoes a dramatic transformation. The gravity surrounding a black hole is of unimaginable strength, dwarfing anything we experience on Earth. This gravitational leviathan warps everything in its vicinity, including light itself. Light, in its essence, is a carrier of energy. However, as light ventures near a black hole, its energy is relentlessly siphoned away by the black hole's gravitational grasp. Consider a sunset, where the sun adopts a warm reddish-orange hue. This occurs because sunlight, as it traverses our atmosphere, scatters and sheds its higher energy blue tones, leaving the redder frequencies to dominate. Similarly, near a black hole, light loses energy, causing it to shift towards the red end of the spectrum. The spaceship, initially displaying its true colors, gradually appears redder and redder as it nears the black hole, as though the black hole is casting a chromatic spell. The second bizarre phenomenon is related to the very fabric of time. According to Einstein's theory of general relativity, gravity can distort time itself in peculiar ways. Imagine this. You're not on the spaceship, but observing it from afar. In this scenario, time behaves differently for you than for those on board. You, the observer, experience time flowing, sun-baked craters of Mercury and the Moon. While the question remains whether these reserves are sufficient to support human colonies, the potential is undeniable. Mars, too, harbors icy secrets at its poles, concealed beneath layers of dust and frost. Even smaller celestial bodies, like Saturn's moon Enceladus and the dwarf planet Ceres, possess icy landscapes. NASA scientists are particularly intrigued by Jupiter's moon Europa, suspecting the existence of a vast liquid ocean beneath its icy shell. Despite being significantly smaller than Earth, Europa might possess an ocean with twice the volume of all our planet's oceans combined. Now, let's journey deeper into the galaxy. In 2009, scientists exploring a colossal cloud of dust and gas at the Milky Way's center stumbled upon an astonishing discovery: ethyl formate. This remarkable chemical compound bestows upon raspberries their delightful flavor and emits a rum-like scent. But the surprises didn't end there. A neighboring region teemed with ethyl alcohol, the very same type found in alcoholic beverages. In fact, this cosmic reservoir contains enough alcohol to provide every person on Earth with 300,000 pints of beer every single day for the next billion years. Believe it or not, scientists have even managed to create a black hole here on Earth. The creation of an in-lab black hole was indispensable for research. Studying real black holes in the vastness of space remains a distant prospect, making laboratory experiments essential. A team of scientists in the Netherlands embarked on a mission to investigate the enigmatic Hawking radiation theory, proposed by the legendary Stephen Hawking. Using atoms to simulate an event horizon, they orchestrated a surge in electron activity, generating a temperature spike that mirrored the conditions of flat spacetime. As particles traversed quantum fluctuations, a ring of infrared radiation materialized around the lab-grown black hole, mirroring Hawking's theoretical predictions. Moving on to a less theoretical, but equally surprising discovery: lunar allergies. During the final Apollo missions, astronauts brought back a wealth of rock samples, thanks in part to the presence of Jack Schmitt, the first and only professional geologist to walk on the Moon. His meticulously collected samples expanded our understanding of the Moon's magnetic field and volcanic history. However, the lunar expeditions revealed an unexpected challenge. Jack Schmitt was allergic to moon dust. The fine clinging powder irritated his sinuses, nose, eyes, and throat for several hours after he removed his helmet. Consider the incredible density of neutron stars, where matter is compressed into an incredibly small space. A mere teaspoonful of neutron star material would outweigh the entire human population combined. To replicate such density, we would have to compress every human on Earth into a space the size of a sugar cube. When we contemplate the vastness of space, Earth and the Moon may seem like close neighbors. Yet the reality is astonishing. All the other planets in our solar system could fit between Earth and the Moon. The average distance separating our planet and its satellite is approximately 240,000 miles. Even if you combine the diameters of all 7 other planets, you'd still have roughly 5,000 miles to spare. In 2011, scientists announced the groundbreaking discovery of a colossal water reservoir in space. This immense body of water, equivalent to 140 trillion times the total amount of water in Earth's oceans, could provide every person on our planet with their own planet's worth of water 20,000 times over. The reservoir was located near a supermassive black hole, actively drawing in matter and emitting intense energy, known as a quasar. The water molecules were formed by the collision of energy waves, binding hydrogen and oxygen atoms together, approximately 12 billion light-years away. Finally, imagine the excitement that rippled through the scientific community when the Curiosity Mars rover captured its first Martian sunset in 2015. Turns out sunsets on the red planet are truly unique. Imagine the desolate landscape of Mars. According to NASA, the Martian atmosphere casts a breathtaking azure hue across the planet. The fine dust swirling in the air acts as a unique filter, allowing blue light to penetrate while blocking warmer shades like yellow, orange, and red. It's a truly alien vista millions of miles away. Now, let's journey to Venus. This sister planet spins at a snail's pace compared to Earth. A complete rotation takes a staggering 243 Earth days, and it rotates in the opposite direction. Yet, despite this sluggish spin, Venus completes its orbit around the Sun in a mere 225 Earth days. How is this possible? Because Venus hugs the Sun much closer than we do. Believe it or not, a year on Venus is actually shorter than its day. Ever wondered why the night sky isn't ablaze with starlight, leaving no dark patches? This question is known as Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers. He reasoned that in an infinite, unchanging, and timeless universe, stars should be visible in every direction we look. However, the universe isn't infinite, static, or eternal. Edwin Hubble's groundbreaking discovery revealed that the universe is expanding. Furthermore, the faint afterglow of the Big Bang tells us the universe is approximately 13.8 billion years old. Imagine all those birthday candles needed. The reason we observe darkness is that the light from some stars simply hasn't had enough time to reach us, or those stars are too distant to be seen. Let's jump to the Apollo 16 lunar mission. Command Module pilot Ken Mattingly experienced a heart-stopping moment when he realized his wedding ring had vanished. The entire crew launched a frantic search within the spacecraft, but their efforts proved fruitless. Then, on the 9th day, during a spacewalk, Mattingly's ring was spotted drifting near the hatch door. Charles Duke Jr. attempted to retrieve it, but missed. Fortunately, the ring ricocheted off Mattingly's helmet and landed safely into Duke's gloved hands. A collective sigh of relief echoed through mission control. It's remarkable they recovered the ring, but countless other items remain lost in the vast expanse of space. Rumor has it that even a toothbrush is floating around up there somewhere. Consider Mercury, already the smallest planet in our solar system, excluding Pluto, of course, and the second densest after Earth. Incredibly, Mercury is still shrinking and becoming even denser. For a long time, Earth was believed to be the only planet with tectonic activity. However, that notion was shattered when the Messenger spacecraft flew past Mercury, providing us with a detailed survey of the entire planet. In 2016, Messenger uncovered fascinating cliff-like formations known as fault scarps. Their relatively small size suggests they are geologically young, indicating that Mercury is still contracting, even after 4.5 billion years since the solar system's formation. About a decade ago, Australian astronaut Luca Parmitano faced a terrifying near-drowning experience during a spacewalk due to an unaddressed water leak. Water had infiltrated his helmet, but the cause remained a mystery. NASA launched a months-long investigation, but the precise reason for the water intrusion remained elusive. In more recent news, astronomers have discovered the most massive stellar black hole ever observed within our own Milky Way galaxy. This colossal space behemoth boasts a mass 33 times greater than our Sun and resides approximately 2,000 light-years away. Until recently, the largest known stellar black hole in our galaxy was only about 20 times the Sun's mass. The average stellar mass black hole typically weighs in at around 10 solar masses. Scientists from the European Southern Observatory's Gaia mission identified this giant black hole by observing a star exhibiting a wobble as it orbited the area. The black hole was named Gaia BH3. Its proximity to Earth makes it the second closest known black hole to our planet. The nearest black hole, Gaia BH1, lurks approximately 1,560 light-years away. This somewhat unsettling neighbor has a mass about 9.6 times that of the Sun, making it considerably smaller than the newly discovered Gaia BH3. Gaia BH3 resides within the Aquila constellation, which from Earth appears to resemble an eagle. Surprisingly, astronomers didn't anticipate finding such a massive black hole lurking so close to Earth and remaining undetected for so long. Of course, we have to admit that even this stellar black hole is dwarfed by supermassive black holes like the one at the center of our galaxy. Imagine the vast expanse of the Milky Way, our galactic home. Deep within its heart, a cosmic titan reigns supreme. Sagittarius A. Sagittarius, a star. This is no ordinary celestial body. It's a supermassive black hole, a space behemoth whose mass dwarfs our own Sun by a staggering 4.2 million times. While smaller stellar black holes are born from the fiery collapse of dying stars, supermassive black holes like Sagittarius AA have a more complex and mysterious origin story. Scientists believe they often arise from the merging of smaller black holes, a cosmic dance of gravitational attraction and